So the next thing that we're looking at in this unit are cubic functions that are written in power form. So we've already looked at cubic functions that are written in that expanded polynomial form, also in factored form. But sometimes cubic functions can be written in what's called power form, which is this one that we have here. Hopefully you'll notice that that looks a lot like turning point form for a quadratic, because it is. Okay, we could also say turning point form for a quadratic is power form as well. Okay, where you've just got your any sort of x terms there are in the brackets to a raised to a power. And when a cubic function is written in power form, what it means is that we can write, or we can sketch our graph of the cubic, and it won't have the appearance of a minimum and a maximum value that you've seen before, but rather it has something called a single stationary point of inflection. Okay, so I'll just erase that. It has a stationary point of inflection. Okay, and that, if you have a look at the graph that we have here, that is that point that we have there at 0, 0. That is what we call our stationary point of inflection. Okay, when it's written in power form, okay, it is this, the coordinates of our stationary point of inflection have the values hk. H is our x coordinate of the point of inflection, and k is the y coordinate of the point of inflection. Okay, what we have here in this particular sketch is y equals x cubed. That is the simplest cubic function that we have. Okay. Now, this simple cubic function with a stationary point of inflection can undergo transformations just like the quadratic, the parabola can. Okay, we've thought through the transformations of y equals x squared as dilations, reflections and translations. Well, we can do the same thing with our simple basic cubic of y equals x cubed. As we saw with the quadratic, the simple cubic can be transformed with dilations. Okay, so if we have y equals a times x minus h cubed plus k, this value of a, that is our dilation factor parallel to the y-axis, just like our parabola. Okay, it dilates the graph, in other words it stretches the graph out vertically, okay, away from the x-axis or in the direction of the y-axis, or we might say parallel to the y-axis. Okay, you'll notice here that I've written here that's sometimes referred to as from the x-axis. Okay, if you go to the textbook and you're answering a problem in terms of dilation, it will always say, you know, maybe a factor of 2 or a factor of 5 or whatever, in away from or from the x-axis. That means the same thing as if we were to say in the direction of the y-axis or parallel to the y-axis. Okay, so here's our information sheet, and if I just scroll through that, what we have here on our information sheet are the graphical transformations of these basic functions that we have. Okay, so we've looked at the quadratic, okay, and now we're looking at the cubic. Okay, and you can see here hk from our formula here, our rule. Hk is our stationary point of inflection. Now, here we have some wording, if you like, for different transformations, and which applies to any function at all. You'll notice that we have a negative out the front here of f of x. So if f of x represents our basic function, if we have a negative out the front of the function as a whole, that will be a reflection of the graph of y equals f of x in the x-axis, or about the x-axis. So if we have some function here, and that's f of x, then if we have a negative, what it's going to do is reflect it about the x-axis. Okay, so the x-axis is the mirror line, and so our original function is reflected in that. So this would be negative f of x. Okay. If we have a negative on the inside here with x, then that's a reflection of the graph in the y-axis, and so it would be this. Okay, so this would be f of negative x. Okay, so it's reflecting it about the y-axis. If we have an a out the front, and that's exactly what we're referring to here, where we have our a out the front of these brackets, okay, that a is a dilation of the graph of y equals f of x by a factor of a in the direction of the y-axis. So you'll notice that we have here described on our information sheet, the wording says in the direction of the y-axis. We can say parallel to the y-axis, or we could say from the x-axis, which just means away from it, okay, which is why the textbooks have it as from the x-axis, but it means the same thing as in the direction of the y-axis. Okay, so it's just really to highlight a little bit difference in wording, but meaning the same thing. If we have a look at the next one here, y equals f of a times x. So you'll notice here if we have our x being multiplied by an a within the brackets, so technically if we have the a instead of being outside the brackets here but actually inside and next to the x, sometimes you'll see that. That is technically a dilation of the graph by a factor of 1 over a. Okay, so even though the x is being multiplied by the a, the dilation factor is 1 over a, and the direction this time is in the direction of the x-axis. So it is that way. Okay, it's horizontally or parallel to the x-axis. You could say from the y-axis. Okay, so just pay attention to those few little things, details, which you need to be aware of. Okay, and whoops. The other thing is here, if our inside the brackets we have x plus b, so if we're adding or subtracting something that's within those brackets, then that's a translation horizontally. Okay, it'll be left or right. So if it's plus b, if you like, that's going to be a translation of b units to the left. Okay, so let's just have a look here. You'll notice in our cubic that it says x minus h. Okay, and because it's got this minus h, that's why the graph is drawn to the right. So it's translated h units to the right. If we had x plus h, it would be translated h units to the left. Okay, so that's something you need to be aware of. Then we've got this plus k is a vertical translation up. If it was minus k, it'd be down. All right, and that's exactly what we have here on this last one. Y equals f of x plus b is a translation of the graph, whatever the function f of x is, b units up. Okay, if it was minus b, it'd be down. So just be aware of that. Study the wording here and look at what that means. If a is negative, so our a value is negative, then the graph of the basic cubic is going to reflect it in the x-axis. Okay, it's flipped upside down. if x is replaced with negative x, then the graph of the basic cubic is reflected in the y-axis, and so it's flipped sideways. And so this particular graph highlights that. So here we've got an example of y equals x minus 1 cubed. But if we have a negative here in front of the x, we've got negative x minus 1 cubed, then it's actually reflected sideways. Okay, what I want to show, I just want to show you something at this point, which is important, is that say we have y equals negative x minus 1 cubed, as we've got there. Technically, what we could do at this point here is take out a negative 1 as a factor. So we could write that as, I'm just going to put extra set of brackets here, negative, we'll take that out. If we do that, this x will become positive, this 1 also will become positive. Okay, so hopefully you can see that what we've got here in this second equation is equivalent to the first one. We've taken out the negative 1 as a factor, but everything inside here is still raised to the power of 3. Now what we could do is apply that power of 3 to both the negative 1 out the front here and also the x plus 1. So what I can do is take it an extra step, and if I've got negative 1 cubed, then that becomes negative 1, then x plus 1 cubed. So this is in fact equivalent to what we've got here. Now hopefully you'll notice here that if we look at this, what we have is now there's a negative 1 right out the front, which is just like saying our a is negative. Okay, in which case it would be flipped upside down and translated. Now if you look at this, it says it's translated to the left 1 unit, okay, which would mean that our basic cubic of y equals x cubed is flipped upside down and translated to the left 1 unit, and that's exactly what this one is too here. Translations, as we said before, okay, our basic cubic y equals x cubed. If we have y equals, in brackets, x plus 3 all cubed, then it's going to be translated to the left 3 units. Okay, still has the same shape. Or if we have x minus 3 in brackets cubed, then it's translated to the right 3 units, and so we have this. Okay. If the coefficient of x is not 1, the equation must be rewritten in the form y equals a x minus 1 cubed plus k, so that we can accurately work out the value of h to see what the horizontal translation is. And so let's have a look at this one, for example. Okay, y equals 2x minus 5 cubed. Just like we did with taking the negative 1 out earlier as a factor, we can take out the 2 as a factor. Okay, so by doing that, you'll notice here we've got the 2 out the front, and then inside the brackets we're left with the x minus 5 over 2, and then close brackets. Hopefully you can see that if we were to expand this, we'd have 2 times x is 2x, and then 2 times 5 over 2, the 2's would cancel and left with minus 5. So by taking the 2 out as a factor, we can clearly see what our horizontal translation is. Okay, they're actually going to be translated to the right 5 over 2 units, or 2.5 units. The cubed here will apply to the 2 and the brackets. So 2 cubed would give us 8. Okay, so we've got 8 times brackets x minus 5 over 2 cubed. This is important. Okay, we can see then that we've got a dilation factor of 8 parallel to the x-axis, parallel to the y-axis, and then horizontal translation of 2.5 units, or 5 over 2 units right. Okay, and so then when we're combining the transformations, this is what we have on our information sheet. Okay, where we've got y equals a outside of x minus h cubed plus k, and so that's represented graphically with that.